has the ability to basically through sonic, not radar, but through kind of like how a bat listens. I'm going to start over since I'm an idiot.
Hey guys, I'd like to go over a little demonstration with you, something I normally would do as a lab in the classroom. So here I am in my classroom and I'm going to run this through with you. So what I've got going on is I have a block of wood that I'm going to slide across the table. I'm going to give it a push and it's going to accelerate and come to a stop on its own because of the friction between its surface and the table. The clicking that you hear is a motion detector. It's a sonic motion detector, and it has the ability to determine how far away the object is because of the time it takes the sound to go there and back. So you'll notice that as I move this back and forth, that the sensor is able to pick that up. So I've zeroed it out. In fact, let's do this. Let's start a new file. And so what I want to do is I want to zero out this position. I want this to be the 0. Not a big deal, but I'm going to go ahead and zero this out. So it now thinks that this is the 0. This should be a, that's a negative position. I want that to be a positive position. There we go. So I want this to be about 0, and I want that to be about a positive 1-ish. There we go. That'll work. Okay, so now what I'm going to do is I'm going to run it through. And tell you what, let's also go to the sensors data collection and let's increase the rate of this thing to let's say 40 cycles per second. That should about do it. So that way when it runs, it collects 40 samples per second instead of just 20. And I'm going to give it a push. It'll be just like that. Ooh, man, I should have been recording. That worked out so well. So let's try that, and I'm going to record and see what it looks like. Well, that looks pretty good. So what are we looking at here? Okay, well, let's take a look. So what we've got going on, let's see, if this must have been my initial push. Its velocity was 0, and then it increased its velocity, didn't it? And then it got to some peak velocity. It got to a peak velocity. That's the moment at which my hand is just about releasing and no longer pushing. So then from here to here, that is where it is decelerating. It is going from a high velocity back down to 0, and it is this part here. In fact, let me highlight it. It is this part here where the friction is taking hold. And you'll notice that it is a curved, right, position versus time graph because it is accelerating. It is a nice consistent acceleration. If you notice that here on this graph, it is a nice line. You can see that it's probably important that I picked up the number of cycles per second so we have more samples during that short period of time. So here's what I'd like to do is I would like to determine what is the acceleration that is occurring in this event. So let's go ahead and take a look. All right, so we've got this section here, and I'm going to look at the velocity graph. What I want to do is I want to take the let's see, statistics, I think is where I want to go, of the velocity graph. Whoa, try that again. Analyze the statistics. Actually, you know what, I'm going to do a curve fit of the velocity graph. And you can see that it's got the brackets around the segment that I had highlighted. And I'm going to do a linear. And you can see that I have the slope. The slope is a negative because it's slowing down. The velocity is changing in a negative direction. A negative 3.3265, and that is my acceleration. That is the derivative. All right, well, that looks good. So I've got that information. I'm going to save that run, and tell you what, I'm going to run a few more runs. So let's start back at the beginning, and let's go ahead and collect some more data. That looks pretty decent. Again, let's select this segment. In fact, I don't need to worry about collecting everything. I just want to make sure I collect the stuff where it's a nice straight line. Go to Analyze, the curve fit for the velocity graph. and I want a linear fit. Negative 3.27, fairly consistent, good. So let's save that run, and let's try it again. Let's do 5 runs. It looks good. Curve fit. Ah, come on, don't be weird. There we go. Don't be that guy. Don't be weird. Negative 3.4, still fairly consistent. Sounds good. That's the run. 2 more. Looks like there's a little bit of a hiccup in there. I don't think I'm too worried about it though, as long as in fact, let's do this. Let's just select this segment and kind of ignore the little hiccup. I'm just concerned about what the slope of that line is. And we're going to choose that linear fit to get the acceleration, right? The slope of the velocity line is the acceleration. A little bit of a larger value that time. Perhaps maybe that's my run that I'm not, maybe I'll strike through that data. Another little hiccup. I wonder if it's this this line that I've got in the table. That's interesting. Got another hiccup. I'll bet it's that line in the table. Well, maybe what I should be doing is picking up all of that data this time. Analyze, curve fit, velocity, linear, 3.36. I have a feeling that I should go back and change that 4th run. Let's go back to the 4th run and let's analyze. Let's select the whole thing this time. Yeah, I think I feel better about it. That it kind of helps average everything out. And it looks like we have some pretty good numbers between all of them. So tell you what I'll do is we will put together all those numbers and get an average acceleration for each of them. And what do we really want to do with all this? Well, we have a force of friction that is slowing this down. It's doing work, in fact, to slow it down. So the work done by friction, the force, which by the way, that force doesn't change. The friction force, other than maybe this line, the friction force stays fairly consistent over the course of its speed. So there's a distance over which it had applied that force. And you know what? We can figure out what that distance is, right? We have a starting point and we have an ending point. So I can determine what the maximum and minimum values are here. So I'm going to go through and figure that out. So let's say for this one, let's do this. Let's select this guy. Or you know what? Let's go back to the run 1. Okay. So for this one, let's select all this data. And I want to select the statistics of the position graph. And I see that there's a minimum of 0.007 and a maximum of 0.952. So I know my displacement is about 0.944, something like that. And if my mental math is right, and it's not, but it's pretty close. And so that's my displacement. So there was that force, and there's an average force. Okay, does it? Oh wait, it doesn't give me the force, does it? But maybe I can figure out what that is, right? Because mass times acceleration is force. I just need that mass. 454 grams, so 0.454 kilograms. Alrighty then. So with that, you have mass, you have acceleration, find the force. Sounds simple enough because there's no other forces acting on it other than gravity and the normal force. This is a fairly flat level table. I'm not too concerned about any little bit that it's off from that. So now that we have the force, that's the friction force. So the friction force is equal to the coefficient times the normal force. The normal force is, well, equal and opposite to the force of gravity in this case, which is mg. You know mass. Find the coefficient. I'll post this data, and I want you to figure that out. So there we go. I just wanted to add a little something fairly quick that I think I had said that I would take the maximum and minimum positions in this space here. But really what I want is I want to look at where I was no longer touching it, right? That's where the velocity was at its maximum. So at that, right about there, I want to know what the position is at that spot, right? So right there, it's 0.335. So 0.335 is my initial position, and then it looks like 0.952 is my final position. So I need to find the change in position and kind of go from there. All right, so we'll see if we can work with that. Now that I'm back in my office, I wanted to take a moment to kind of bring all those ideas together and sort of coalesce all of the things that I had talked about and have a more cohesive train of thought moving forward. So firstly, we have this idea where we have the friction force, which is in this case the stopping force. It is equal to mu k, because it's a kinetic friction, times the normal force. Now because it's a flat level surface, we have the force of mg acting down, and we have a force that is the normal force acting up, and they are equal and opposite in this case. Not an action-reaction pair, but they are opposites. There's a moth. And so if I want to find the coefficient, I would just simply take the friction force, which is the force that we determine, I'll get to that in a second, divided by the normal force, and that's going to equal the coefficient of kinetic friction. Now how do we determine the friction force? We didn't measure that directly. Well, if I have this box, there is a force impeding its motion, causing it to slow down. That is the friction force. Well, what other force is there? What about the force of my hand? No, not the force of my hand. You see, I pushed it initially for just a moment, but once I released it, then my hand was no longer applying a force onto it, and the only force still acting on it was the force of friction. And during that time, and that's the time that we're focused on, so when you look at the blue line here, the part that's sloping downwards, that's what we're focused on. And so it is that part that we're looking at where the force of friction is the only force acting on it in the x direction, and so therefore this is the force impeding its motion and slowing it down. This is equal to ma. So we effectively have ma over mg, right? So that means that the coefficient of kinetic friction is ma over mg, and in fact the mass doesn't even matter. So acceleration over 9.8. So whatever the acceleration is over 9.8 will give us the coefficient in this case. Okay, so now what? Awesome, we can find the coefficient of friction. What I'd also like to determine though is I want to show that the work done is equal to the change in kinetic energy. So I want to show and prove that work is equal to the change in kinetic energy. I want to prove that the force times the distance is equal to the change in 1/2 mv squared. So it's 1/2 m delta v squared. That's a delta right there, I promise. It is. It's a triangle, kind of. I'll just fill it in. Sure, why not? And so what we're going to do, I would like you to also take this force, multiply it by the distance, the displacement. Again, remember that we have a segment where the peak
force, if you're looking at the blue line here on the graph, the peak velocity is what we're focused on. That's this, because it went from that peak velocity down to 0. And so what I did is I went back in and I went to analyze statistics for the position to figure out where it should have started and where it ended. And remember, I looked where I had lined up where the velocity was at its maximum. That's my initial position. And then final position is where it came to a stop. I determined what the maximum velocity was. Out of anything, that's probably going to be the most unreliable bit of data because it was at that velocity for just an instant. And I had determined the slope of this blue line as well. Okay, so that's all the data that I had collected, and I'd done that for all the runs. I also added a couple extra runs as well for good measure. I also wanted to add a run that it particularly went slower because I want to also show if this is a constant force, if I had a different velocity, right? So if I were to maybe try and get my eraser out, and if I had a different velocity, right? So let me just plug in v, put parentheses around it. If I were to double the velocity, 2 squared is 4, so this would become 4v squared, right? So I've effectively made the entire right side of the equation 4 times greater. That means that if the force stays the same, the displacement would be 4 times greater. I want to see if that relationship is in fact true. So there's a couple of other things I'm trying to do here. I want to see if, gotta keep it square. I want to see if, in fact, the work done is equal to the change in kinetic energy, and I also want to evaluate as to whether the changing velocities does in fact represent that the displacement would be an exponential change. Okay, so we are looking for that information. We're trying to evaluate that. So I'm posting the data that I collected, and I want you to try and go through on an Excel spreadsheet. That is the best way to go about it, and see if you can actually determine these things. Determine what the percent difference is between the work done and the change in kinetic energy. I would say that if we're within 5%, that's probably a pretty good value, and that would mean that there is some sort of statistic significant separation there, or that it's, in fact, it's not separated. So it's statistically significantly the same. I'm not a statistician. That's the worst wording of anything I've ever heard in my life. It's been a long day. So with that, I would like you guys to go through and I'll clarify anything else. Reach out to me for questions, and I hope that there's something to be gained from it. So until then, until next time, I'll see you. Whatever. I'm out. Peace.